Right, so what we're going to do is we're going to learn how to construct the feasible region, and that's the area that you needed your solution to be in from the previous video, basically. So we're going to learn how to construct that yourself. So I'm going to start off by plotting some lines. Presumably you can plot y is 5.
Presumably.
Go for it. I mean, just a rough sketch is fine, just as an idea.
It's a horizontal one.
Yes, it is.
Oh my goodness. Right.
Yeah, that's it. Excellent, and excellent labelling.
Thank you.
Well done. Because there's going to be loads of lines, so keeping those labels on is really important. Y equals x.
That's nice and easy. Without running out of this.
That's the one. And, okay, shall we come back to that next one and do the x is 13? Perfect. Okay, so they're obviously relatively easy. The next one's slightly harder. The way I would recommend to do this, the 3x plus 5y is 60, is to find out what's happening on each of the axes and then join it off. So when x is 0, what is y? When y is 0, what is x? And then join them off.
Okay. X is 0. It's got 0 plus 5y, which is 60.
Yep.
So y is 12.
Yep.
So we know we've got that point.
Yep.
And then y is 0. We've got 3x plus 0 is 60. So x is 20.
Yeah, yeah, I agree with that. Yep, and then you can plot those.
20, 0, 0, 12-ish.
Yep. There we go. And you might recognise those lines from the previous video as the lines that we were using for the feasible region, but we're going to pretend that we've got no idea
Never seen them before.
what the feasible region. So this could be the feasible region in here, or maybe this is, or maybe this is, or maybe it could be anything. It could be literally any of these could be the feasible region, and we need to put the shading on, and we're going to shade around the region to see which of these is the region, basically. So when you see your inequalities, and these are the inequalities that are going to give us the region, what you do first of all is you just pretend they say equals, y equals 5, x equals 13, 3x plus 5y equals 16, and you draw them as lines. Then you think about the inequality. So this is the strategy we're going to use for working out which side we want. We're going to sub x is 0 and y is 0 into each of the inequalities and then see whether or not it's true. So if you take that first one, sub y is 0 into that inequality. That's it. Now is that true or not?
No.
No. So the origin is not on the side of this line that we want. So the origin is down here. And the line that we drew is the y equals 5, this line here. And the origin is on the wrong side because this is not true. Not true. So the origin is on the wrong side. So the side of the line that we want is not the side with the origin in.
So it's getting rid of the side that we don't want.
Yes, so we're going to get rid of the side that we don't want with these little dashed lines that we say we do not want to be on that side, because that test that we did for the origin, it didn't work. It came out wrong. So that's the basic test we're going to do. So do you want to try the next one? Okay. So sub in the origin.
So is less than 30, which is true.
True.
So we do want that side of the line.
Yes.
So
We want the side of the line with the origin in it.
So we don't want that side.
That's the one. We don't want that side. Great. And next one. Sub in the origin.
Right. So 0, 29, 60.
Is that true?
No.
Not true. So we don't want the side of that line that contains the origin. We don't want...
Well, this is our line, isn't it?
Yep, that's right. And we don't want the half with the origin. That's the one. We don't want that. Do not want. Now at this stage you might think it's fairly obvious what the feasible region is, and you're probably right, but obviously don't guess. Keep going. Okay, so let's do the last one and just check. So sub the origin in. Is that true? Yes, that's true. 0 is in fact bigger than or equal to, in the sense that it's equal to 0. So we do want the side of the line with the origin in.
It goes through the origin.
This is, a major problem. it goes through there isn't a side of the line with the origin in. That's the problem. There is no such thing as the side of the line with the origin in because the line goes through the origin. So the test totally fails and breaks down. But we can use the same idea, we just need to pick a different point to test.
Okay.
We can't test something that's on the line because it's not either side of the line. But we could test something like this point, 1, 0. X is 1, Y is 0. We could test that instead.
I think that's 4, but that was good.
Is it 4?
Yeah.
Oh, it is 4, you're right. 4, yep, 4.
Try 4. Why not? Okay.
So X is 4, Y is 0. So we sub that in. Is that true?
True.
True. So same principle applies, but we have to
So
test a different point. That's
We
all.
want the side that has that point on it.
Yeah, because that's true. So that's the correct side of the line.
So we don't want that side.
That's it. And then you can see our region has been revealed. Yep. And this region has got an edge here. It actually goes across there at the bottom because we didn't want this bit. And it goes up here and this goes down here. So it's got 1, 2, 3, 4 vertices. So if we were now doing the vertex method for optimizing, we would work out the coordinates of all 4, A, B, C, D, and then put all 4 into whatever function we were maximizing and see, or minimizing, and see which one works. Or if we're doing the ruler method, we would plot our objective line, our profit line, or whatever it's called, cost line, objective line, and then we'd move it parallel and see what the last vertex or the first vertex that it hits is, and then we'd know that's what we wanted as our coordinates. Okay, so see if you can do one all on your own. So 2 of these have already been done for you. The y less than or equal to 50, that's already been shaded.
We've already done that.
Yeah, x bigger than or equal to 40, that's already been shaded. So we've got rid of the bits that are less than or equal to 40. All the x's less than or equal to 40 we don't want. And we've got rid of all the y's that are bigger than 50.
Yep.
We want to be less than or equal to 50. But we're being asked to put 2 more lines on. So we start by pretending it says equals.
Right, so I don't want to plot that on just by plotting it. So I'm going to use points. So when x equals 0, when x equals 0, 4y, less than or equal to 60.
Yeah, it's easier to go, I think, at the beginning with just equals. So
Oh,
just,
yeah.
do you remember, like the first thing we did was just pretend it says equals in the line? Yeah, so it's almost like we're dealing with 3x plus 4y equals 360, so that we get a line, and x equals 2y, so we get a line, and then we'll think about the inequality.
It's 360.
Yes.
Yeah. So y is, brain engaged, 90.
Yeah. I'm just doing it on the calculator. Yeah, 90. Yep, 90.
So we've got 0, 90 is the point.
Yep.
And then y is 0, so 3 equals 360. X is 120.
Yep. I just did that so that we can get the line drawer.
120, 0. Right, so
Okay.
let's put the points on.
There. So it goes from there.
And goes,
Yeah. Line drawer. Might make it a bit nicer. Like this.
perfect.
Okay.
Right. Do the region first or do you not do the
Well, there is something that you should do before you do the next one, or before you do the shading, or before you do anything. You label it. Fantastic. Because when we do our vertex method or our ruler method, we're going to come across corners and vertices, then we'll need to do simultaneous equations, and if we lose track of which equation is which, also you lose marks if you're not labelled. So the line is now labelled. I think it's a good idea at this stage to say, let's do the shading while you've got that line in your head and you're working on that line. So this is where we're going to sub in 0, 0 into the inequality and see whether or not it's true.
So we're back using this one now, aren't we?
Yes, that's right.
So we've got 0, less than or equal to 6, which is true.
True. Yeah.
So we want the side that has the origin in it.
Yes.
So we don't want that side.
Perfect. And that's that one done.
Good.
Next one.
Which around should we
Well, you could do, what did you do here? You said, you started off by saying, when x is 0, what is y, and when y is 0, what is x? And then that gave us coordinates on the axes and then joined them up. So, same approach. When x is 0, y is 0, exactly. So that gives us at least one coordinate.
But then when y is 0, x is also 0.
Yeah, you get the same coordinate. It doesn't matter, just stick something else in.
We've got that, isn't that?
Yeah, y equals a half x.
So we know then that for every one we go along.
Yeah, you could
the
think of it.
x-axis, we've got half a one.
You could think of it as across one upper half, the gradient is a half. But essentially, when you're doing that, if you look at what you'd be doing down here, you'd be going across, say, to 10, and then thinking, how far up will I go? I'd go up half as far because the gradient's half, and that would give you this point, and then you join them. So what you're trying to do there is find a second point so you can join it. And I think with this particular equation and this particular graph, possibly what would be easier is to just not rearrange it, leave it in the form it was in, and say, what about, we've done x is 0, y is 0 doesn't help, but what about, I don't know, x is 40? Then y would be 20, and then we can take that information and say that's here on the graph. And then we've got our second point somewhere that's really nice and helpful, and we can then join those points up with that line, which obviously I will immediately label x equals 2y, nicely labelled. So really, it's just, you need 2 points. It's easiest to find what's happening on the x-axis, what's happening on the y-axis, but if it goes through the origin, you need a second point. So just stick anything, stick in x's, whatever you fancy, find out what the y would be, or the other way around, and then that gives you a coordinate. You can join that to the origin and you're done. So, we need to shade.
So put the origin in. But again, the origin, it sits on the origin, isn't it? So
Yes.
we need a new point.
Yes.
So, shall we have 40, 10?
Yeah, you could do. I always choose something on an axis. So one of them's 0. Just because then you're subbing something really obvious in, but you could have any point. You could have any point at all. So yeah, so you've subbed this coordinate that you've chosen, 40, 0, which is down here, and it's been subbed into the inequality, and that's given you this, which is rubbish.
Absolutely.
Lie. So, what does that tell us?
But we don't want the side with that.
Exactly, yeah.
So we don't want any of that rubbish there.
Perfect.
I know what that region is.
Yay! There is your region. So our region has got this shape in this case. It's got 1, 2, 3, 4 vertices. If we were doing the vertex method, we'd have to find coordinates of all of them and stick them all in this function at the top that we're trying to maximise. If we give us some room, now that we've got our feasible region, actually I think we can be a bit more clever with that and do something. Make it all disappear quickly? No, maybe not. I can't do that. Okay, so we've got our feasible region all sketched out. Just to remind you, let's plot the objective line. The line we would use is the ruler line. We won't bother going through all the simultaneous equations and stuff, but just as a reminder, what do we do with that line p equals 60x plus 20y?
Well, we can't plot it as it is, can we?
Nope.
So we're going to have to choose a random p
Yep.
that works. So
Yep.
it's got to be useful.
Yeah.
So, thinking on my feet. 20?
Yeah, try 20. I mean, p can be anything. You just pick anything. Okay. So, when x is 0,
20 equals 20y.
yep,
So y is 1.
yep,
And that's not going to help me at all. When y is 0, it's not helpful at all. 20 equals 60x, so x is 1/3.
okay. And then looking at the scale of our graph, really, no matter how much we zoom in, I think it is going to be difficult to plot those points.
So can we make that 200?
Yeah, we can make it anything.
Make that
I
200.
mean, what you've done isn't wrong, it's just I can't,
Can't
the
then use
scale
it.
isn't big enough to use those points. Calculator.
Three, it's fine.
Is it 3?
No, it's not.
200 divided by 60. 3 is 3 1/3. Oh, I don't like that.
Don't like that either.
No, I don't like that either.
No. New one?
Yeah, something that you can divide 60 and 20 by. What about 600?
Okay, so we had 600. 6x plus. Right, when x is 0, 600 is 20y.
So that's y is 30 according to the calculator.
Yeah,
Okay, that's fine. That's there.
good. And then when y is 0,
No, that's not there. Yes, that is there. That is there. No, yes, yeah, that is there. I thought I'd got it on the wrong axis, but no, it is there.
x
Okay.
is 10.
Which is okay. Actually, it's still not brilliant, is it? Because look,
It's tiny.
the x is
isn't
still
it?
tiny, but I think we can probably.
And if you've got a ruler, you're only lining it up to that line, aren't you? So
Yeah, exactly. So I think we can. Oh, that wasn't a line. I was expecting a line to happen there. Okay. So it's something like this, basically. Is the ruler line?
Yeah.
I mean, to be honest, I still think we've kind of screwed that up, really. Look, it's not wrong, but the line is so far away from the feasible region that when we're moving it with a ruler, there's every
Yeah.
possibility that, I mean,
You're gonna go wonky
that you're going to go
and-
wonky.
yeah.
I mean, this isn't because it's a line, but you might accidentally tilt it slightly. And it would. I think what would have been better in an ideal world is if we'd ended up somewhere like that.
yeah,
So, or maybe even like down here somewhere. So if we'd chosen whatever number we would have had to choose here, oops, in order to get whatever we would need to choose here for P, in order to get the
Yeah.
X and Y to come out
to
nice.
get that to get like 60 or something.
Yeah, exactly. But it's fine. And anyway, we can move our one, can't we?
Yeah.
So, so we would want to maximise this according to the question. So you go, how far right can you go? And you go, and then obviously that's this last one here, this vertex is going to be our optimal one. And then we would work out the simultaneous equations of this line x equals 2y and this line, which we handily labelled. So we know what we're doing. Simultaneous equations, find the coordinates, stick them back into P to find out what the maximum is. Obviously checking whether or not we need integer values. If so, what's the closest integer inside R? Brilliant.